For task 1, the goal of this task is to analyze the co-occurrence patterns of different symptoms within the disease profiles. So specifically, the task aims to identify combinations of symptoms that frequently appear together in the same disease. So this is our code. Here we just imported all the relevant libraries, and we read the dataset over here. So you can have a brief understanding of how the dataset looks like. And we decided to count the number of unique disease names, and we found that there are 41 diseases. We also did the same to find the number of unique symptoms, and we found that there are 131 symptoms. And we also found that in our data cleaning process that there are a few symptoms that have the same meaning, but they're written differently. So in order to normalize them, we came up with a list of symptoms that we found that had similar meaning, such as shortness of breath and breathlessness. They mean the same thing. So we had to normalize them to make our analysis better. And here's our normalized data set. So for each disease, you can see all the symptoms that were shown for the particular disease. So for example, fungal infection, you can see that there are 4 symptoms, and the rest will be shown as NAN. And we did the same thing again, and we found that there are 92 unique symptoms. We then conducted the a priori scan with minimum support value of 0.01 to maintain maximum inclusivity. And for rule generation, we used the value of 0.7 to retain rules that are strong for analysis. And after doing so, we managed to find the rules for each of the disease. We printed the results, and here's what we have. So for task 2, we did our data exploration. So this is how our data set looks like. We look at the class balance plot. We created box plots for the feature distribution by diagnosis. Here are the distribution plots. And for our data cleaning, we removed any unused and weird columns. We removed the outliers using IQR. And for feature transformation to categorical levels, we split them into these 3 levels using these 3 strategies: uniform, quantile, and k-means. Over here, we define the sequence semantics per patient. So we converted each patient's feature vector into an ordered sequence based on their importance. So instead of grouping the sequences like high radius mean and high parameter mean and so on, we group them to the top k features as ordered item sets with the maximum sequence length of L. For our data analysis, we applied the sequential pattern mining algorithms such as the GSP, and we did it by splitting the sequence into malignant and benign, flattening the item set for a simple contiguous sequential pattern mining. Here's the GSP algorithm. And we mined the patterns for malignant and benign groups. And we inspected the top patterns by length. We also ran the sensitivity analysis. So we look at the effect of binning strategy. We look at the effect of outlier removal. And we also look at the different binning strategies on original dataset that has the outliers. We also varied the K and minimum support to find longer patterns.
For task 3, we implemented a healthcare-oriented diagnostic tool that predicts the likelihood that a breast tumor is malignant or benign using machine learning and iterative user inputs. We began by loading and cleaning the data, mapping the diagnosis column into binary labels, 1 for malignant, 0 for benign. From there, we focused on a created subset of 6 top features identified earlier in task 2. These features capture the strongest signals linked to tumor severity. Next, we split the data into training and test sets with stratification to maintain class balance. We use a pipeline that standardizes the feature scales and then train a random forest classifier, which uses 200 trees and balanced class weights to handle the mild class imbalance. After training, we evaluate the model using multiple metrics, including accuracy, precision, and F1 score. The result shows strong predictive performance and a solid ability to detect malignant cases. We also compute feature importances from the random forest, which helps us link back to our task 2 findings. Finally, we export the train pipeline and selected feature list using Dropleap, making the model ready for deployment in our Streamlit application. This is our breast cancer risk prediction app. Here, we have a user interface that allows healthcare professionals to use these sliders to input tumor feature values. After inputting the values, we can then press the predict cancer risk button. Here, we have predicted the tumor to be malignant, with an estimated probability of malignancy being 100%. Let's try other values. As you can see, the estimated probability of malignancy has dropped. Here, we can compare the above values with dataset averages. We also have an optional visual comparison for any selected features. For example, texture worst. As you can see, our value is above the benign value, but somewhat comparable to the malignant mean. In conclusion, our app successfully demonstrates a functional and interpretable cancer risk prediction pipeline and a clean user interface for healthcare professionals to use.